No.
Well, if you introduce yourself.
Well, good afternoon, ladies and gentlemen. I'm Roger Roback. I'm sure you all know me by now. But anyway, I volunteered to give this talk on cosmochemistry, which is something that most people have never heard of. So let's see, what do we do now?
You just the arrow keys on each side. You got the screen up here. So just
Okay. Okay, the objective of this talk is humans want to know. Well, what do we want to know? We want to know where we came from and how life actually arose on Earth or in the universe. So what is cosmochemistry? Cosmochemistry is how molecules essential to life were formed from basically the elements in the universe, in the early atmosphere of the Earth. Anyway, oops. Humans want to know, this is what we're going after. Where did we come from and what we are made of? If you recall, Neil deGrasse Tyson has said, we come from stardust. Well, essentially, we may not come from stardust, but we come from the stuff that stardust is made out of. Cosmochemistry, the definition, the science was actually named by Dr. Harold C. Urey, who did the first experiments in the field. He showed us that we can get something from nothing. In other words, making molecules from atoms. Cosmochemistry was named by Harold C. Urey, who was a physical chemist, and he has a very interesting background for people living here in Montana. That we're back. Okay. Harold was born in Indiana, and he was in a very fundamental Christian church, and that were a Anabaptist and New Testament only belief. So he had a very stringent upbringing and went to a Amish grade school. From there, he went to a small college in Indiana where he gained a teaching certificate and became a middle school teacher for a while. And then he moved on. He entered the University of Montana in Missoula in 1914. And unlike the universities of the time, the University of Montana was coeducational, both in students and teachers. Urey earned a Bachelor of Science degree in zoology in 1917. So I'm going to skip ahead. World War I, Harold was a conscientious objector and did not want to be in the front lines carrying a rifle. So he went into the business of making explosives for the US military. I don't know how many 1,000 tons of TNT he was responsible for manufacturing, but anyway, after the war, he went back to Montana to teach chemistry. And after teaching in Montana for a while, Harold went on to University of California at Berkeley and completed a doctoral degree under Dr. G.N. Lewis, who was a very famous physical chemist at the time. And he was always interested in how life, he was always interested.
Hold on.
Harold was always interested in how life began and also in the moon. He was very curious about whether the moon and Earth shared a common origin. In other words, was the moon part of Earth at one time? And this was a question that followed him through his entire career in chemistry. But he was a physical chemist, and he was trying to find ways of how do you determine something like that. If you have a sample from the moon and a sample from the Earth, how can you determine that they were from the same origin? So Harold was a pioneer in atomic isotopes. He set out to find evidence of neutrons in 1931, and through some work with the National Bureau of Standards, they isolated a compound or a atom known as deuterium, which is called heavy hydrogen. You notice the lower right-hand structure there. That is what you would call the Bohr atom, the model that they came up with early in the 1930s to describe what atoms looked like. They were composed of a proton and an electron. They knew about that, but they did not know much about the neutron. So by isolating deuterium, which had one neutron, and it was different atomic weight from hydrogen, he showed that there were neutrons. So for that discovery, Harold was awarded the Nobel Prize in chemistry in 1934. Then after he was, excuse me, after doing that work, World War II came along, and because of his knowledge of atomic isotopes and the purification of atomic isotopes, he was tapped to direct the manufacture of uranium-235 to create the atomic bomb, which he did by the creation of Oak Ridge National Laboratories in Tennessee, where most of the uranium or the first bombs were manufactured. You see the picture on the right, the group of the Manhattan Project chemists and physicists, and J. Robert Oppenheimer was involved. You see he's in the second from the left in the picture, standing there, and Harold is over on the right side. But anyway, he was a very close collaborator of Robert Oppenheimer. And here is the group with Harold second from the left, with Oppenheimer further to the right. After the war, Harold did not want to be involved in weapons research any longer. As it says, no more bombs. And he was worried that the production of the bomb and the uranium that he was manufacturing was going to be strictly held by the military and could lead to even worse conditions and circumstances than we had during the war. So he was fundamental in the creation of the Atomic Energy Commission. And he was also brought before the McCarthy hearings in the 1950s for possibly being a communist because of his pacifistic beliefs. So he decided after that to focus his attention elsewhere. And that was in the study of the early Earth and the introduction of cosmochemistry. So he asked a bunch of fundamental questions as, what molecules were here in early Earth. Of course, the conditions then were no oxygen in the atmosphere. It was primarily ammonia, methane, water vapor, and hydrogen. So he was questioning that. And you might ask, how did I become interested in cosmochemistry? Well, when I was a graduate student at the University of Wyoming in my second year of grad school in chemistry in 1970, my laboratory was on the third floor of the chemistry building. So I trudged down the stairs to the basement where the science library was located. And at the base of the stairs and just coming out of the library was the Dean of Arts and Sciences, Dr. Gerald Myers, and this elderly gentleman. And I was introduced to him, and it was Dr. Harold Urey. And he was there to give a talk on cosmochemistry. So that kind of has stuck with me for a long time. So he asked the essential questions of why planets don't have an atmosphere of oxygen. Well, it has to do with plants, and we all know that photosynthesis is what generates oxygen from carbon dioxide. I mean, that's why all the eco-freaks are running around screaming about, trying to get rid of the carbon dioxide in the atmosphere and not wanting us to drive automobiles with diesel engines or gasoline-powered engines. So in about the early 1950s, Harold was a professor of chemistry at the University of Chicago. And he was talking with one of his graduate students, Stanley Miller, about the early Earth's atmosphere and what they could possibly devise as an experiment to see what happened with the conditions of an early Earth atmosphere of methane, ammonia, hydrogen, and water vapor. Stanley Miller devised an apparatus to do some experiments. And this is the famous Urey-Miller experiment, which was devised to find out where the building blocks of life came from. The essential building blocks of life are amino acids, from which proteins are formed. And we all know about amino acids because a lot of us take supplements of various amino acids to maintain our muscles and to maintain our health. So since the atmosphere was only methane, ammonia, and water vapor, here's a picture of the Miller apparatus. What they did, first of all, they had about a 500 milliliter, or let's say 16-ounce volume flask with water, and a 5-liter flask up here. That's about 1¼ gallons of for vapor. And they heated the water vapor into a flask filled with only ammonia, methane, and hydrogen. And then they had 2 electrodes in there, and they fired sparks through this system for about a week. And after a week, all the liquid that they had condensed out of the system had turned a dark brown. And they took samples out, and the experiment was run for a week. They analyzed it, and they were able to isolate several amino acids from the gamish that they had in the brown liquid. They used a technique called paper chromatography. which is, you can see it's a tank with a glass rod horizontally, and they have long strips of filter paper, and they would spot the little tiny amounts of the gamish on the top of filter paper, and this is what is called descending paper chromatography, is what they were using. This the apparatus isn't really shown correctly. That the solvent would be flowing downwards from a dish that they would have at the top. But anyway, this kind of gives you the idea of what's going on. If you take a piece of paper towel, for example, and you just dip it in water, you notice that it will spread throughout the paper towel. And it's the same principle as that, if they have a solvent system that isn't just water, that may be a mixture of various other organic chemicals, such as phenol or acetic acid and water or whatever. They had various mixtures that they would use, and they would allow these spots that they put close to the solvent, they would then be carried along with the moisture front that was from the diffusion of the solvent through the water, through the paper, and various compounds move at various rates. They don't all move all as one spot. That you may have noticed this if you had a piece of paper towel and you wrote something on it with a ballpoint pen and you get it wet, you'll notice that the colors separated. That's the principle that we're looking at. So anyway, they ran the experiment and they found, in addition to a lot of other compounds, they found glycine, alanine, and aspartic acid, which are all three essential amino acids for making the proteins of life. So what they had done, they had created biological molecules from a non-biological source. So the something for nothing approach. They also isolated a dipeptide, glycylglycine, which is sort of a shortest possible protein analog. And basically they did some fabulous work. Mainly it was Stanley Miller's creation, but he was strongly supported by Harold Urey in this particular project. That the initial paper was submitted to the scientific magazine Science in 1953 after they completed the work in 1952. And for some reason, Science just held off on publishing it. They never published it until they got a very angry, nasty letter from Harold Urey wondering why they were not publishing what he thought was a very significant step in the study of the chemistry of life. So this brings us to why were only 3 of the amino acids essential for life found in the mixture that they made. Then wouldn't there be a lot more? Well, there were other experiments made by Stanley Miller, and unfortunately, for a lot of the better work to be done with the newer modern instrumentation, Stanley Miller had a stroke in 1999 and passed away in 2001. And after he had his stroke, he turned his entire laboratory at University of California in San Diego over to Jeffrey Bada, who is now a professor of chemistry at the Scripps Institute of Oceanography in San Diego. So at that point, the analysis of things by chromatography had advanced a lot in the intervening nearly 50 years. But they now have instrumentation where you can inject samples into a device called a high performance liquid chromatograph and do the separations. And it seemed that pawing through the stuff that was in Stanley Miller's laboratory, he found the original 1952 samples in little vials and subjected them to high performance liquid chromatography. And he found 17 of the essential amino acids for life in that mixture. The ones that were notably missing were all the essential amino acids that contain the element sulfur. Oops. Anyway, Jeffrey Bada included sulfur dioxide and also hydrogen sulfide in some of the mixtures to repeat the experiments with the same apparatus. And lo and behold, they got much better yields of all the other amino acids, as well as finding methionine, cysteine, and cysteine, the 3 sulfur-bearing amino acids that are found in mammalian proteins. So basically, they found that by doing these experiments, they were able to basically create the essential amino acids for living organisms. As an aside, Dr. Bada is now working with deep sea ocean vents to find out if these vents will produce amino acids. And lo and behold, they have. And in fact, in much higher yield than doing this atmospheric mimicking of lightning. So the theory being that you need the hydrogen sulfide, that seems to catalyze the reactions and make them much more effective. Where do we go from here, though? We've started with nothing and made the amino acids that are essential for life. What are the next steps? Well, I saw on YouTube about a month ago, a fellow named Anton Petrov has a YouTube channel, and he does like almost a daily astronomy talk. And one of the things that he was talking about at the time was the appearance of the outer Kuiper belt planetoids, the Eris and the some of the other ones that I can't even remember their names. And they noted with the Hubble Space Telescope that they are not just white reflective planetary planetoids, that they are all pretty highly colored. And they did the infrared spectroscopy using the James Webb Space Telescope, not the Hubble, but the James Webb Space Telescope. They did the IR spectra of the surfaces, and what they found were that the colors were attributed to polynuclear aromatic hydrocarbons. And I talked to an astronomy professor from State University of New York about 20 years ago down in Casper when he gave a talk. He said that they found that a lot of the meteoroids that they've detected are loaded with polynuclear aromatic hydrocarbons, and they also had determined that most comets are loaded with polynuclear aromatic hydrocarbons. And these are interesting because they are involved in the steroids like testosterone, estrogen, basic structure of all these steroids, cholesterol included, contain the elements of phenanthrene, which was one of the elements of one of the compounds that they were finding in the spectra of Eris and some of these other dwarf planets that are out there in the Kuiper belt, and that's the source of all of the comets that are entering the inner solar system. So it seems that maybe life didn't originate here on Earth, but it was brought to Earth from the cosmos. We just don't know. But one of the other ongoing theories in the scientific community is their seeding of life throughout the entire universe with the from what they call panspermia. So this is there's a lot to do, but when I looked at this work, as a professional chemist myself, I was wondering what experiments would I be doing if I still had a laboratory and were active. And one of these things is that optical activity of amino acids is something that maybe you don't understand what it is, but if you have a solution of an amino acid and you shine polarized light on it, you will find that if it's these ones that are not optically active, they do not rotate the plane of light. In other words, to see the light coming out of a sample is irradiated. Thus, if we're looking at it through polarized glasses, it will be rotated. If it's a optically active amino acid, you will not see the full intensity of the light until you rotate the polarizing filters. So this is what I'm interested in, is how you could make optically active amino acids from these basic systems. And how many of you here are into mineralogy of any kind? Okay. Well, there's different forms of quartz crystals. There's right-handed quartz crystals, and there's left-handed quartz crystals. I was thinking of trying to build an apparatus that had maybe some crystals inside that would possibly be of one-handedness, pure one-handedness, and see if that would result in the formation of optically active amino acids. In other words, making either a D or L form of amino acids. That's where I would be going if I had a laboratory. So anyway, I'll just wrap things up here. I probably jabbered too long already. So anybody have any questions? Yes, sir. An optically active amino acid is if you take carbon has 4 valences. In other words, you know what a tetrahedron is? Okay, carbon has its bonding to the carbon atom tetrahedrally. In other words, the bonds stick out in 4 different directions, and a right-handed compound and a left-handed compound. In other words, if you take 3 different elements and bond it to carbon, you can bond it 2 different ways. That will have you will not be able to superimpose them. One will be right-handed, and one will be left-handed. And that's what you're looking at when you're talking about optical activity. Huh? Not spinning, it's just the way they're constructed. They are stable compounds, and it's just a matter of if I had a molecular model kit, I could build something very simple, and you would be able to see that they're chemically the same, but they're physically different.
So like if you shined optically actively, means that if you were to shine a certain kind of light on it, it would
rotate the light.
Rotate the light.
The plane of the light. In other words, if you have like a Venetian blinds, consider that to be a polarizing system. And you want to have light come through, and you have the one set of blinds with the light shining through it, and the other set of blinds at the other end is at a different angle. You're not going to see any light on the other side until you get the other set of blinds aligned with the light that's coming through. Well, what happens when you have a solution of an optically active compound? It rotates the polarization.
Just see right through it.
It does it right through it, and that's why one of the most expensive and essential instruments in a chemistry laboratory for people doing work with amino acids is what's called a polarimeter. You can actually measure the rotation of the light with a given amino acid. It's just basically you find one wavelength of light, you shine it through with one set of polarizers, and then the detector is at the end of the other system with another polarizer, and they rotate the second polarizer until you get maximum intensity of light coming through. So it can actually measure the rotation. Yes, no.
What would be the significance of that?
Well,
What does that mean?
all
How can we use that?
all life as we know it is what they call the L configuration. Every amino acid known in living animals is of the L configuration. That means it rotates the plane of polarized right to the left. Another case is carbohydrates. They're also optically active, and they all have the D configuration, but that's a completely different can of worms to open up.
Maybe there's other right-sided compounds somewhere else in here.
That's possible, it depends on what happened on the individual plant. That's why I have been arguing online with people at the Mars Society that one of the most essential pieces of equipment that we need to take along on the first expedition to Mars is if we do find anything like amino acids, we have to know if they're optically active and of the L configuration, which means that life, here on Earth is, similar to life on another planet.
What's the next step into life from the amino acid stage?
There's a lot of people working on it because they're looking at what causes these molecules to aggregate and to grow into peptides or proteins, and also how membranes start forming to form, cells, this sort of thing. It's a huge field, and I haven't really kept up on it. I'm retired after all. So,
Yeah.
you all know this part.
Thanks for your
Thank you, Roger.
You know, okay, that's good.